Okay, so last week we talked about correlations very generally. We talked about positive correlations, negative correlations, and no correlation. And that's a really good general way of describing what a correlation is. But today we're going to get a little more specific. In addition to talking about whether it's positive or negative or has no correlation, we're going to assign a number to each correlation that tells us how straight the line is. So if you have a scatter plot that's going up, we say it's positive, but there's a difference between a scatter plot going up where the points are sort of far away from each other and it makes like a general going up cloud versus if we have points that are going up and they are in a perfectly straight line. And so we use a number to say basically how straight is the scatter plot. And that number we use is called the correlation coefficient. And the variable that we use for the correlation coefficient is a lowercase r. The variable r is the correlation coefficient. So the correlation coefficient is between -1 and +1. So r is a value between 1 and +1 that measures the strength of the linear association between two variables. Now that's the official textbook definition, but in general, you can think of this as how straight is the scatter plot. That's really what R is. How straight is the scatter plot? So because all of our numbers are between -1 and +1, we can make a number line here to sort of talk about the straightness of a line. So we'll put on one end -1 and on the other end +1, and we'll put 0 right here in the middle. So if we have a situation where r equals -1, -1 is a perfect correlation, meaning all of our points in our scatter plot are exactly in a straight line. We call this a perfect negative correlation. And so what it looks like is this. We do our x-axis and our y-axis. A perfect negative correlation is a scatter plot in which all of the points are in a perfectly straight line. -1, perfect correlation, and it's negative, so that means it's going down. If r equals +1, that is a perfect positive correlation, which again means all of the points are in a perfectly straight line, but now they're going up because it's a +1. Like that. 0 exactly in the middle is no correlation. And no correlation means they're not in a line at all. Could be completely scattered, or instead of being completely scattered, they could be just in a shape that's not a line. For example, if it was in a U shape, that would also have no linear correlation. So the closer the R value gets to 1 and -1, the closer we are to having a perfectly straight line. Now, it's unlikely that you're going to have a scatter plot where the data is perfectly straight. In real life, that almost never happens, that your data would be perfectly straight. But you could get close. For example, if I were to give you, let's say, an R value of negative 0.8. That's closer to negative 1 than 0. So negative 0.8 might look like this. It's negative, so it's going down. And you can see that the dots aren't in a perfectly straight line, but they're pretty close. If I compared that to R equals 0.4, negative 0.4, that is also negative, but negative 0.4 is closer to 0 than it is to negative 1. So my data would still be going down, but would be much more spread out like that. You can kind of see that it's going down, but it's also, the points are not really super close together. It's more difficult to see. So the closer it is to negative 1 or positive 1, the stronger the correlation is, meaning the more straight the line is. Except for our poor guy 0, no correlation at all. So it's possible to get the exact R value from a table of data. If I give you a list of numbers, a list of coordinates last week, and you graphed it on a scatter plot, there is a mathematical process for finding out exactly what the R value is. That process is not easy, and you will not have a good time doing it. So instead, we're going to use Desmos, and this is the site that I showed you last week. So go ahead and open up a browser window and go to desmos.com. And just like last week, we're going to add in a table with some scatter plot data. I'm going to go ahead and give you the coordinates here. And I'll give you just a minute to put those in there. If you have a printout of the notes, this scatter plot is on page 5. If you'd like to follow along, page 5 in the notes. And I'm going to go ahead and adjust my axes. My x-axis goes from 0 to 10. That sounds good. And we'll have the y-axis go from, looks like our lowest y is 12 and the highest is 29. So let's go like 10 to 30. Sounds good. There we go. So I'll give you just a minute to get those points put in. And then a quick refresher, I showed you this in last week's class, but the way that we can get the software here to give us the best fit line is by clicking on the plus sign and selecting expression. And we're going to do Y1. And then the tilde here is approximately. We're going to do MX plus B. And the X needs to be this one. Right here, Y1, you just literally type Y and the number 1. And then do the tilde, which is on my keyboard, it's just below the escape key. You do shift and that button to do the, it's like the approximately, because we're approximating a best fit line. And we're doing MX plus B, but instead of X, we're doing X1. me come take a look. Shift and this button. There you go. And then it should be mx plus b, but our table had x1, not x. It had x1, so do mx1 plus b. And so what we're telling Desmos to do is take that table we just made in x1, y1 and find a best fit line, which is what it's trying to do. What we talked about last time was how to find the slope and the y-intercept, which are on there. The m and the b that Desmos gives you are the slope and the y-intercept. But also, if you look just above that, there's our r. R is negative 0.9733, meaning this is a pretty straight line. -1 would be perfectly straight. This one's clearly not perfectly straight. The points are off by a little bit. It's close. It's close to perfectly straight. Okay. So let's adjust this a little bit. I'm just going to delete what's in the table here, and I'm on page 6 with this. And I want to show you an example of weak and positive correlations. So I'm going to do 10, 25. We'll do 20, 62, 30, 75, 40, and 12, 50, 75, 60, and 80, 70, and 100, 80, 20, and 90, 15. And you'll notice that as I do that, the y equals mx plus b automatically adjusts, which is nice of it. And I'm going to make my x and y axis go from 0 to 100. Maybe by 10s is better. Let's do that. So this is an example of a weak correlation. And you can see that our R value is negative 0.065, which is pretty lousy. I typed in a number wrong. That one's 190. There we go. Sorry, so R is 0.108. That's a pretty weak correlation. Are those points going up? Yeah, they are, but not really anywhere close to a straight line. So we would say that this has a weak correlation. Okay, let's try a moderate correlation. I'm going to keep the same x values, but I'm going to make a new list of y values here. Okay, and we can add another expression for y2. I think that's a good idea. Just watch this. So that line right there, the line that I did in blue, has an R value of 0.631. That's what we would describe as a moderate correlation. Take the other one off. That's a moderate correlation. It's going up, but the points are definitely closer together. And then finally, let me give you an example of a strong correlation. Go ahead and do one for y3. remove the other ones. There's a strong correlation. It's going up and the points are very, very close together. Strong correlation. So the first one, let me go back to it. Weak, moderate, strong. And you can see that, really see the difference between weak and strong. They're strong, look like they're almost in a perfectly straight line, right? Weak, you can barely even tell which direction they're going. And then moderate, I can tell that they're going up, but see this point right here? 40, 12. I wonder what would happen if I took that point out. What do you think would happen if I removed this 40, 12? Would the correlation become stronger, weaker, or stay the same if I took out 40, 12? Let's find out. Oops, I think I deleted an extra one. Looks like it got a lot stronger when I replaced that 12 with a number that was a little closer to the line. How about that? I think 40, 12 was making things bad. So 1 point can make quite a big difference. That's called an influential point. An influential point is one that can really change the entire makeup of the graph just by removing it. So far, so good? Okay. Take a look at page 8 if you've got the notes. If you don't have the notes, relax. I'm going to put all the data up here. Somebody's recording rainfall for a period of 6 days. So I'm going to put in 1, 2, 3, 4, 5, 6. They record how much rain there is for each of 6 days. Do you think there's going to be a strong correlation between the day and how much rain there is if I record it 6 days in a row? Is that going to have a strong correlation? Why not? Sure, because the day probably doesn't have anything to do with the rain if it's 6 days in a row. If this was like 1 day in each month, maybe we'd see a correlation. Maybe certain months get more rain than others, but because it's just 6 days in a row where there's a lot of rain or not very much rain, we don't expect there to be a huge correlation. So there's our scatter plot. We need to go ahead and adjust our x-axis and y-axis to be able to see all of the points. So let's go ahead and make our x go from 0 to 10, make our y go from 0 to 2. There it is, and it certainly doesn't look like there's a strong correlation. I mean, it looks like it's positive, right? We can see that it's going up for the most part, but those points are not very close together. If I wanted to see exactly how strong this model is, I can do that. We'll do y1 is approximately mx1 plus b, just like we've done before. And our R value here is 0.24. How would you describe a correlation of 0.24? That's weak. We would say that is a weak correlation. Really, I'd say anything between 0 and 0.3, I would consider weak. And I'd say anything from 0.7 up, I would say is strong. In fact, let's go ahead and put that in our notes. That seems like an important safety tip. We're going to say in our notes that if R is between 0 and 0.3, that is going to be a weak correlation. I'd say if it's 0.3 and up to 7, we would describe that as being a moderate correlation. And anything higher than that, which would be from 0.7 up to 1, we would say that is a strong correlation. And this applies if R is negative as well. So that would apply for negatives also. Between 0 and negative 0.3, we'd say weak. Between negative 0.3 and negative 0.7, we'd say strong. I mean moderate. And between negative 0.7 and negative 1, we would say strong. Now, one of the ways that correlation can get you in trouble is that a lot of times people think that because two things are closely correlated to one another, that they must cause one another. Correlation is not causation. Uh, 10. Just because two things are correlated does not mean one causes the other. Consider this. If I were to measure the number of ice cream cones that were sold in one day and the number of hats that were sold in one day, would I find a strong correlation between those two things, between ice cream and hats? I think I might. If it's really hot outside, I will sell more ice cream, and people will also want to buy hats to protect themselves from the sun. I think there would be a correlation between people who buy ice cream and people who buy hats. But I don't think buying ice cream causes you to buy a hat. I don't think anybody eats ice cream and goes, oh, you know what would go great with this ice cream? A hat. Both of those things are caused by temperature. If the temperature is very high, you're more likely to buy ice cream and more likely to buy a hat. There might be a negative correlation between ice cream and beanies, for example. It's really cold outside. I don't want ice cream, but I might want a beanie or a toboggan. When there was a big polio epidemic in the early 20th century, a lot of people thought that polio was caused by ice cream because there were big polio outbreaks in the summer. So they thought ice cream, and then they thought like maybe the fuzz from peaches was contaminated and causing polio. And there was no relationship between polio and ice cream or polio and peaches. It was just because since the outbreak happened in the summer, people were eating ice cream anyway. So ice cream didn't make people get polio. I've also noticed a correlation between the number of pirates and the average global temperature. Seems like the fewer pirates we have, the hotter the planet becomes. Average global temperature increases as pirate population decreases. I think if we brought the pirates back, we could stop this whole global warming thing right now. My personal favorite correlation is the correlation between the number of TVs a household owns and your life expectancy. As it turns out, owning a lot of TVs is closely correlated with living for a very long time. But I don't think that means that you could buy a bunch of TVs and then live longer. Although those things are correlated, owning TVs does not make you live longer. In fact, conventional wisdom would say the more TVs you have, probably the worse effect it has on your life expectancy because you're sitting down watching TV instead of doing something productive. But the thing that causes both of those is wealth. If you have a lot of money, you can buy multiple TVs. And if you have a lot of wealth, you can buy really good medical care. So money is the thing that would make both of those happen. So similar correlation between owning a pet and living longer. People who own pets have a average life expectancy that's maybe 2 years longer than everybody else, 2 or 3 years longer if you own a pet, but probably not having a pet in your house makes you live longer. Otherwise, people who ran animal shelters would be immortal. It just means if you can afford to have a pet, you can probably afford good medical care. And again, wealth causes those two things to happen. I think there's also a correlation between Nicolas Cage movies and the bee population. The bee population? Let me see if I can find it. Here we go. Let me share this with you. This website is called spurious correlations, meaning things that are correlated but don't actually have anything to do with one another. There's an extremely strong correlation between how much money the US spends on science, space, and technology and the number of suicides by hanging, strangulation, and suffocation. Seems unlikely that spending a bunch of money on science and technology increases the rate of suicide, but they are correlated. Oh, I'm sorry, it wasn't bees, it was people who drowned by falling into a pool. If Nicolas Cage appears in more movies, there are more drownings in swimming pools. Thanks a lot, Nicolas Cage. Strong correlation there. Cheese consumption is strongly correlated with number of people who died by becoming tangled in their bed sheets. The divorce rate in Maine is strongly correlated with the consumption of margarine. The age of Miss America correlates with murders by steam, hot vapors, and hot objects. Revenue generated by arcades and computer science doctorates awarded. Non-commercial space launches is correlated with sociology doctorates. Oh, as more people eat more mozzarella cheese, we get more engineering doctorates. This is pretty scary. People who drowned after falling out of a fishing boat is correlated with the marriage rate in Kentucky. The oil we get from Norway correlates with drivers killed in collisions with railway trains. Letters in the winning word of the Scripps National Spelling Bee is correlated with the number of people killed by venomous spiders. Turns out that if the Scripps National Spelling Bee winning word has fewer letters in it, fewer people die from venomous spiders. So if you're a good speller, spiders won't get you. So as you can see, quite a strong difference between correlation and causation. Do not get the two mixed up. Just because two things are related does not mean one causes the other. Over the summer, there was a sudden spike in people who were buying toilet paper and people who were buying flour. I couldn't find toilet paper or flour in the store, but it seems unlikely that someone bought a bunch of flour and was like, after I cook with this, I'm gonna need some toilet paper. Those two things were probably not causing one another. No, flour that you cook with. Couldn't find flour or toilet paper or sanitizing wipes or eggs for some reason in the store. But I don't think that those things caused one another. I don't think somebody was like, oh, you know, it'd go great with eggs, hand sanitizer. There was another outside factor that was causing both of those. They did not cause each other. Does anyone have any questions about correlation or causation?